All right, let's jump right in. We're not just talking about another predictive model today. Oh no, we're going way more ambitious. We're going to architect a system that's designed from the ground up to generate real, actual scientific value. We're building an engine for discovery.
And really, this quote says it all. This is the core philosophy. Every single choice we're about to look at, from how we handle data to which models we use, it's gotta be justified. Does it make the system more trustworthy? Does it help us discover something new? And is it cost-effective? This isn't just some academic exercise. It's about building a serious tool for real-world science.
So, why even bother building this thing in the first place? Well, because the way we normally do scientific discovery, especially in fields like chemistry, is a grind. It is incredibly slow, it burns through a ton of cash, and honestly, the success rate for finding a new, useful compound can be pretty depressingly low. This engine is built to attack those exact problems head-on. So where do we begin on this journey? It all starts with the data. And let me be clear, this part is absolutely non-negotiable. You've all heard the phrase garbage in, garbage out, right? Well, in science, that's not just a mistake, it's a catastrophic failure. A data-first approach is the only way to build a foundation that we can actually trust.
Now, what's really interesting about this slide is the sheer discipline it represents. We're taking all this messy, raw stuff, data buried in PDFs or just jotted down as lab IDs, and we're forcing it through this really rigorous pipeline. We pull out the useful info, give it structure, we validate it, and, this is crucial, we add all the important metadata, like the temperature or the pH of the experiment. And that final step, versioning, that creates these unchangeable data sets. It means we can always trace the result all the way back to its exact origin. No black boxes. And look, this isn't just about being neat and tidy. This whole process creates immense value. Reproducibility is the absolute bedrock of science, and this pipeline basically guarantees it. It cleans out all the noise so we're not accidentally comparing apples to oranges. And it brings up a huge business point. These clean version datasets, they are a form of intellectual property themselves. They're a tangible asset.
Okay, so we've got our pristine data foundation all set up. Now, how does the engine actually learn from it? The key here is to make it think like a whole team of expert chemists, where each one is looking at the problem from a slightly different angle.
And that brings us to a really central question. I mean, chemistry is its own language, right? It's a language of structures, properties, interactions. Just feeding a machine a list of features isn't going to cut it. So how can a machine possibly develop a deep, nuanced understanding of what molecules are all about? Well, the answer is a multi-view approach. As you can see here, the system doesn't just rely on one way of looking at a molecule. It uses fingerprints to see the small local pieces. It uses things called RDKit descriptors to get the big picture properties, like weight and size. Then you have graph neural networks to understand that intricate web of how atoms and bonds connect. And it even uses language models like MolBERT to get a feel for the grammar of chemistry. Each view captures a different signal that the others might miss. It's like having a whole panel of experts. But the key here is being strategic. It's all about choosing the right tool for the job. You don't always need a sledgehammer to crack a nut, right? So on one hand, for a lot of problems, a simple combo of XGBoost and fingerprints is cheap, it's fast, and it's surprisingly effective. It's the perfect starting point. But on the other hand, when we need to dig into those deeper, more complex patterns, that's when we bring in the heavy hitters, like GNNs and transformers. They cost more to run for sure, but the insights they can pull out are just on another level. And we don't just pick one model and call it a day. No way. The engine uses what are called ensembles. Think of it like this. It's like getting a second, third, and fourth opinion from different specialists. By combining the predictions from all these diverse models, we can smooth out the errors, cancel out individual biases, and land on a final decision that's way more trustworthy than what any single model could give you on its own.
All right, so the engine has learned from the data, it's crunched the numbers, but a raw prediction, just a number on a screen, isn't enough. It's not the end goal. So now we've got to shift focus to the output. The whole point is to deliver something a scientist can actually trust and, most importantly, act on.
This statement right here, it's pretty much the core principle of the engine's entire output strategy. Think about it. If a domain expert, a real chemist in a lab, doesn't trust what the machine is telling them, the whole system is worthless. It doesn't matter how accurate the model is on paper. Trust is the final and most important metric. So how do we build that trust? Well, one of the most powerful ways is through something called uncertainty quantification. This is basically the model's ability to tell you how confident it is. A model that can say,
hey, I'm really sure about this one, but honestly, I'm just kind of guessing on that one, well, that's incredibly valuable. It keeps us from wasting thousands of dollars and weeks of time in the lab chasing down a low-confidence hunch from a machine. And this all comes together in the final product, a complete decision-grade package. A scientist doesn't just get a number, they get the whole shebang. They get the probability of success, that uncertainty score we just talked about, SHAP explanations that show why the model made its prediction, and even visualizations of the key parts of the molecule. It even provides an evidence chain from a knowledge graph and suggests an experiment to run. It's not a prediction, it's a complete, actionable, scientific hypothesis. Okay, now for what I think is the most powerful part of this entire system. We've built the engine, sure, but how do we make it a compounding asset, something that gets better and better over time? The answer is the value flywheel. It's a feedback loop that makes the engine smarter with every single experiment that gets run. Here's how it works. It's actually a pretty elegant loop. First, the engine proposes new molecules to test. Second, the lab runs the experiments. And here's the magic part. That new data, whether the experiment was a huge success or a total failure, gets fed right back into our pristine data pipeline. The engine then retrains on this new information and it gets smarter. And the cycle just keeps repeating, accelerating the pace of discovery more and more over time.
And listen, this isn't just some cool theoretical idea. This flywheel has a massive, and I mean massive, real-world impact. We are talking about a 5-fold, a 5x, reduction in the cost it takes to find one successful new compound. Just think about what that really means for a second. For the same budget, you get 5 times as many shots on goal. That is a staggering improvement in efficiency, and it directly translates the system's smarts into real, measurable ROI. So what you end up with is a system that isn't just a static tool. This flywheel turns the discovery engine into a living, compounding asset. The more you use it, the better it gets. The core data set gets richer and more valuable, the models become more accurate, and the lab becomes way more efficient, focusing its precious time and resources only on the most promising ideas. And that brings us right back to the central idea, and it's a question really worth thinking about. What are we actually building here? You know, it's pretty easy to build a system that just spits out predictions, but the real challenge and the real value is in building a system that produces trustworthy, actionable, scientific claims. And that right there is the difference between building a toy and building a true engine of discovery.